Welcome to Lecture 8. This week we're going to talk about matrices for linear transformations and similarity, and then we'll completely change topic and I want to start talking about numbers, in particular complex numbers. First, let's talk about matrices for linear transformations. And let's start with an example. We talked briefly about this idea at the end of last week's lesson. Suppose that we have a linear transformation from R2 to R3, and suppose that this satisfies that T maps E1 to the vector 5, minus 7, 2, and it maps TE2 to minus 3, 8, 0, where E1 and E2 make or form the standard basis for R2. And then the example asks us to find a formula for this linear transformation. If we know what T does to the basis vectors in the domain, then we know what it does for any vector in the domain. Why? Because any vector in the domain can be written as a linear combination of the basis vectors. If X is any vector in the domain, then we can write that X is x1 e1 plus x2 e2 for some numbers x1 and e2. Now, because T is linear, that means T of X is x1 T of e1 plus x2 T of e2. And we know T of e1 and we know T of e2. They're written in the yellow box at the top. So all we need to do is to substitute these in. We get 5x1 minus 3x2, and then minus 7x1 plus 8x2, and then 2x1. Or we can write this as a matrix multiplied by the vector x. We have the matrix 5 minus 3 minus 7, 8, 2, 0. And this is the matrix that I'm interested in this section. This is the matrix where the first column is T of E1 and the second column of the matrix is T of E2. This is the matrix for this linear transformation. Let's write this down more generally. Let's suppose T is a linear transformation from Rn to Rm. Then the theorem says there exists a unique matrix A such that T of X is equal to A multiplied by X, such that T is a matrix transformation, and that this is true for all vectors X. Because we're mapping from Rn to Rm, matrix A must be an M by N matrix. And in fact, we have a formula for this matrix. This is the M by N matrix where the first column is T of E1, the second column is T of E2, and so on, where E1, E2 up to En are the standard basis for Rn. Or to say it another way, Ej is the jth column of the identity matrix In. Let's prove this. So just as we did in the first example, any vector x in the domain in Rn can be written as a linear combination of E1 up to En. And then because T is linear, straight away we know that T of X must be x1 T of E1 plus x2 T of E2 plus dot 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 plus xn T of X, so T of En. So we exactly get the matrix that the theorem said multiplied by X. We exactly get the matrix where the first column is T of E1, second column of T of E2, and so on. This proves the existence part of the theorem. This proves that this matrix always exists. But we're not finished yet because the theorem said that this matrix is unique. So we need to prove that as well. Let's suppose that we have two matrices. Let's suppose we know that T of x is AX and we have that T of x is equal to BX. We need to prove that this implies that A and B are the same matrix. But we can do that like this. If we calculated T of EJ, of course that's A of EJ and B of EJ, but A of EJ is just the jth column of A, and B EJ is just the jth column of B. So the jth column of A must be exactly the same as the jth column of B. But that's true for all J. So that proves that A must be the same matrix as B, and then we're finished. For any linear transformation, there exists a unique matrix. And this unique matrix is called the standard matrix for T. And the way we write it is square bracket T square bracket. Another example, an example I've taken from a textbook. Find the standard matrix A for the transformation T of x is equal to 3x. This transformation just takes any vector in R2 and it multiplies it by the number 3. So T maps E1 to 3E1 or 3, 0. So that tells us that the first column of our matrix must be 3, 0. And our transformation maps E2 to 3E2 or the vector 0, 3. So that tells us that the second column of our matrix must be 0, 3. And then we're finished. That's all we need to do. Let T from R2 to R2 be the transformation which rotates each point anti-clockwise about the origin by an angle of phi. So looking at the picture at the bottom, the vector 1, 0, we rotate this anti-clockwise by an angle of phi, and we get to the point cos phi sin phi. Or if we started with the vector 0, 1, we rotate this anti-clockwise and we get to the new vector minus sin phi, comma cos phi. So, as the solution says, 1, 0 rotates to cos phi sin phi, and 0, 1 rotates to minus sin phi cos phi. And that gives us the two columns of our matrix. The first column is cos phi sin phi, and the second column minus sin phi cos phi. We'll talk more about rotations later, but first let's talk about reflections. Let's suppose first we reflect the whole xy plane about the x-axis. So whatever is up here goes down there, what was down there goes back up, and so on. Reflect everything by the x-axis like this. What happens to E1 and E2? Well, E1 doesn't change. E1 was 1, 0, and then after we do our reflection, it's still at 1, 0. But T reflects 0, 1. 0, 1, which was originally pointing upwards. When we do the reflection about the x-axis, it points downwards. T of E2 is 0, minus 1. And that gives us the two columns of our matrix. First column is 1, 0, and the second column is 0, minus 1. The standard matrix, square bracket T square, for reflection about the x-axis is 1, 0, 0, minus 1. Or instead of doing reflection about the x-axis, we could do reflection about the y-axis. Now the vector E1, that's the vector 1, 0, if we do reflection about the y-axis, it reflects to minus 1, 0. E2 stays at E2. So the standard matrix for this reflection is first column minus 1, 0, second column 0, 1. We don't have to reflect only about axes, we could reflect about any lines. For example, let's suppose we reflect about the line y equal to x. Then the vector which E1, which started at here, reflects to 0, 1, and E2 reflects to 1, 0. So the standard matrix is 0, 1, 1, 0. First column is green, 0, 1. Second column, the orange column, is 1, 0. Or let's suppose we do reflection about the line y is equal to minus x. We look to see what happens to E1 and E2, and then that tells us the two columns of our standard matrix. I'll leave that one for you to check. Let's talk about rotations now. Let's suppose we rotate anti-clockwise by an angle of 90 degrees. So we start with the green vector here, and we start with the orange vector pointing upwards, and then we rotate everything by 90 degrees. We have our new green vector, T of E1 is 0, 1, and we have our new orange vector, minus 1, 0. And then as soon as we got that, we can write down the standard matrix for this rotation. Or I could rotate by 180 degrees. I'll leave that for you to check. Or I could rotate by 45 degrees. Or I could rotate by any angle. We looked at this earlier. Let's suppose we rotate by an angle of theta in the anti-clockwise direction. Then the vector 1, 0 rotates to cos theta sine theta, and the vector 0, 1 rotates to minus sine theta cos theta. So we have the standard matrix for this rotation. We could do contractions and expansions. Look at the picture. Let's suppose we squash everything horizontally. If we do horizontal contraction, then the orange vector stays as it is, no change. But the green vector, which was originally the vector 1, 0, gets squashed or contracted to a new vector k0 for some number k, depending on how much we squash this. The standard matrix for this horizontal contraction is k0, 0, 1. Or instead of contracting, we could do expansion. Let's suppose we stretch everything horizontally. Again, E1 maps to K0 and E2 stays the same at 0, 1. So we have the same standard matrix, but this time K is going to be a number bigger than 1 because we're stretching. We could do the same thing vertically, of course. Vertical contraction or vertical expansion. We could do a shear. A shear means grab hold of this and then pull it this way. By K. If we do this shear, E1 doesn't change. The vector 1, 0 maps to the vector 1, 0. But E2 does change. E2 gets pulled to the right. The vector 0, 1 maps to K1. As soon as we know these, we know the two columns of our standard matrix. So we can write down the standard matrix. And one more idea. Orthogonal projections. Let's suppose we want to squash or project everything onto one of the axes. Let's suppose first you take the whole xy plane. I've only drawn a little bit here, but we're doing the whole xy plane, and we're going to squash everything or project everything down onto the x-axis. What happens to the two basis vectors? Well, E1, no change, that stays where it is, but the vector 0, 1, which was just here, after we squash everything down, it just ends up as the point 0, 0. So the standard matrix for projection onto the x-axis will be 1, 0, 0, 0. Or, of course, we could do the same thing, but projecting onto the y-axis. Take the whole xy plane and squash everything from the left and from the right. Squash everything onto the y-axis. Then E1 maps to 0, 0, and E2 doesn't change. E2 stays as 0, 1. We have our standard matrix. Okay, that was an introduction to matrices for linear transformation. And now let's get into the real meat of this section. Let's start talking about a matrix for T relative to two bases. This is a more difficult idea. So now I'm going to slow down. Let's suppose V is an n-dimensional vector space. Let's suppose that B is a basis for V. Let's suppose W is an m-dimensional vector space, and let's suppose that C is a basis for W. We're going to suppose that T is a linear transformation which maps from V to W. So we have something like this. We have our linear transformation T, which maps the vector x to the vector T of x. X is a vector in V, which is an n-dimensional vector space. T of x is a vector in W, which is an m-dimensional vector space. Now, for x, we could write down its coordinates relative to the basis B. And that would give us a vector in Rn. Rn because V is n-dimensional. And we could do the same thing for T of x. We could write down the coordinates for T of x, but now with respect to the basis C. This would give us a vector in Rm because W is m-dimensional. Now the idea here is we want to find a matrix for T relative to these bases. So in other words, we want to find a matrix A which maps the coordinates for x relative to B over to the coordinates for T of x relative to C. Or more precisely, we want to find a matrix A such that if we multiply x, so if we multiply A and the coordinates for x relative to B, we obtain the coordinates for T of x relative to C. And if we can do that, then instead of doing T, we could do it this way. If we're starting at x and we want to finish at T of x, we could go from x to its coordinates, and then from its coordinates for x to the coordinates for T of x. And then if we know the coordinates for T of x, then we know T of x. So instead of just doing T, we could do these red arrows. Okay, so let me just repeat myself. We want to find an m by n matrix A such that A multiplied by the coordinates for x with respect to the basis B is equal to the coordinates for T of x with respect to the basis C. So some notation first of all. Let's suppose B, the basis for capital V, is the set containing the vectors v1, v2 up to vn. Remember, V is n-dimensional, so this basis has n vectors in it. And similarly, let's suppose that our basis for capital W is the vectors w1, w2 up to wm. M because W is m-dimensional. If you're following along in your textbook, have a look at page 307 for the theory that we're going to be doing now. Okay, so in the yellow box, I've written what we want. We're trying to find the matrix A such the formula in the yellow box is true for all vectors x. Well, in particular, this should be true for v1. And it should be true for v2. This should be 2, not s. It should be true for v3, all of the way up to this should be true for vn. But remember, v1 is 1 times v1 plus 0 times v2 plus 0 times v3, etc. So the coordinates for v1 relative to the basis b is just a vector 1, 0, 0, 0, 0. So taking the first one, taking A multiplied by the coordinates for v1 relative to the basis b, which is just this vector, this should be equal to the coordinates for t of v1 with respect to the basis c. Or to write this the other way, the coordinates for t of v1 with respect to c is equal to A multiplied by the coordinates of v1 with respect to b. That's some matrix we don't know. We know it's going to be an m by n matrix, so write it like this, multiplied by the vector 1, 0, 0, 0. But if we multiply this matrix by this vector, then we just get the first column of this matrix. So that means that the first column of this matrix must be the coordinates for t of v1 with respect to the basis c. We could do, instead of doing this for v1, we could do this for any of the vectors in our basis. The second column of the matrix that we want is just going to be the coordinates of t of v2. And all of the way up to the nth column of the matrix that we want must be the coordinates for t of v2 with respect to c. So we found the matrix that we want. The m by n matrix that we want is this one. First column, coordinates of t1, t of v1. Second column, coordinates of t of v2, and all of the way up to nth column, coordinates of t of vn. This matrix is called the matrix for t relative to the bases b and c. And we denote it like this. That's square bracket t square bracket c comma b. Now this might look a little bit wrong to you first of all because we're mapping from v to w. The domain v has basis capital B and the target w has basis c, and yet we're writing c on the left and we're writing b on the right. The reason we write them this way round, b on the right, c on the left, is so that in this formula, it's the matrix for t relative to the bases b and c multiplied by the coordinates for x relative to the basis B is equal to the coordinates of T of X relative to the basis C. Notice that if we write it this way around, we have the B's next to each other. We can sort of imagine that if we do B's next to each other, they can sort of cancel out, and we'll just end up with 1C. So that's why it's this way around. Okay, so two formula that are going to be important to us. I'm writing these in the yellow box at the top. The matrix for T relative to B and C. This is the matrix where we know what each column is. The first column is the coordinates of T of V1, the second column is the coordinates of T of V2, and so on. And the way that we use this is by doing matrix for T relative to the bases B and C multiplied by coordinates of X is equal to the coordinates for T of X. Let's do some examples. First of all, I'm going to leave it for you to prove that if we have a matrix transformation and if we're using the standard bases, then the matrix for T of A relative to the bases B and C is just A. If we're using the standard bases, like we did in this example, we don't have to write them. Instead of writing C and B here, we can just leave them off and just write square bracket T square bracket. Because we just have the standard matrix for T. Standard matrix means the matrix if we use the standard bases. Another example, let T be the linear transformation from P1 to P2, so that's polynomials of degree 1 or less mapping to polynomials of degree 2 or less. And this linear transformation is going to be the transformation which takes any polynomial in P1 and it multiplies it by x. So, for example, if our polynomial is 1 plus x, we multiply this by x and we get x plus x squared. Find the matrix for T with respect to these bases. And these are the standard bases for P1 and P2. So this question could be written another way. It could be written as find the standard matrix for T. So first we want to see what does T do to V1 and V2. What does T do to the polynomial 1? It multiplies 1 by x to give x. But that's 0w1 plus 1w2 plus 0w3. So the coordinates of T of V1 are going to be 0, 1, 0. And what does T do to V2? V2 is x. Multiply that by x, we get x squared, which is the same as 0w1 plus 0w2 plus 1w3. That means that the coordinates for T of V2 are going to be 0, 0, 1. Let me say that again. For T of V1, we have 0, 1, 0. So the coordinates are 0, 1, 0. And for T of V2, we have 0, 0, and 1. So the coordinates of T of V2 are 0, 0, 1. Now we've done all of the work. As soon as we know what T does to V1 and what does T do to V2 in terms of coordinates, we have our basis. So we have our matrix. The matrix for T with respect to B and C is the matrix 0, 0, 1, 0, 0, 1. That's the first column, coordinates of T of V1, and second column, coordinates of T of V2. Another example. Let T be this linear transformation. This is one we looked at earlier, is it? Possibly. This is a matrix transformation with the matrix 0, 1, minus 5, 13, minus 7, 16. But then we're asked to find the matrix for T with respect to different bases B and C, where V1, V2, W1, W2, W3 are written at the bottom. So what do? We need to calculate T of V1, T of V2, and then we need to find the coordinates of T of V1 and T of V2 with respect to the basis C. Before I do that, let me just note that if we were using the standard bases on R2 and R3, then the answer would just be the standard matrix. That's the matrix we were given in the question. But we're not using the standard bases, we're using different bases. So we're going to obtain a different matrix. Okay, so what do we do first? First, we need to calculate T of V1 and we need to calculate T of V2. And I leave those for you to check. I also leave it for you to check that T of V1 is equal to W1 minus 2W3 and T of V2 is equal to 3W1 plus W2 minus W3. So let's just assume that you've checked that, and let's assume that I haven't made a mistake here. As soon as we know this, we can write down the coordinates of T of V1 and T of V2. Looking at T of V1 first of all, we have 1W1 plus 0W2 minus 2W3. So the coordinates here are 1, 0, minus 2. And then looking at T of V2, the numbers are 3, 1, minus 1. The coordinates are 3, 1, minus 1. And then that's the hard work done. As soon as we have these, straight away we can write down the answer. The matrix for T with respect to B and C is the matrix where the first column is 1, 0, minus 2, and the second column is 3, 1, minus 1. So we have two different matrices for the same linear transformation. We have the standard matrix on the left, and then on the right we have the matrix for T relative to these new bases, B and C. That's two different matrices for the same linear transformation. Next, let's talk about linear operators. Let me remind you that if our domain and our target are the same vector space, then the linear transformation from T from V to V is called a linear operator. If we're using the same basis on both the domain and the target, then instead of writing square bracket T square bracket B comma B, we can simplify this and just write square bracket T square bracket B. And then the formula is the matrix for T relative to the basis B is the matrix where the first column is the coordinates of V1, the second column is the coordinates of V2, etc. And the way we use this to change coordinates to coordinates is square bracket T square bracket B multiplied by square bracket X square bracket B is equal to T of X square bracket T of X, square bracket B. Let's talk about identity operators. Let's suppose V is a finite dimensional vector space, any finite dimensional vector space, and let B be a basis for V. We're going to be considering the operator I from V to V, which maps every vector X to itself. But then if it maps every vector to itself, then it does the same thing for V1 up to Vn. I of V1 is V1, I of V2 is V2, etc. What is the coordinates of I of V1 then? Well, it's 1 V1, 0 V2, 0 3, V3, etc. The coordinates of I of V1 is just going to be 1, 0, 0, 0, etc. So the first column of our matrix for I is going to be 1, 0, 0, 0, 0, etc. In other words, the matrix for I relative to the basis B is just the identity matrix. And that's true for every single basis that we choose. As long as we use the same basis on the domain and on the target, the matrix for the identity operator will be the identity matrix. Think about this linear operator from P2 to P2. T takes a polynomial P, and instead of being P of X, it calculates P of 3x minus 5. So just an example, if we start with the polynomial 2x plus x squared, every x we have to replace by 3x minus 5. So instead of 2x, we get 3x minus 5, and instead of plus x squared, we get plus 3x minus 5 squared. I'll leave it for you to check that this and to prove this really is a linear operator. But in this example, we're asked to do two things. Find the matrix for T relative to the basis B, where B is the standard basis, 1x x squared. And then question 2, use this to calculate T of 1 plus 2x plus 3x squared. So, question 1. First, we need to see what does T do to the basis vectors. T of 1 is 1. If we take x and we replace x by 3x minus 5, we just get 3x minus 5. If we take x squared and we replace x by 3x minus 5, multiply it out, we get 9x squared minus 30x plus 25. So the coordinates of T of V1, well, that's 1 times 1 plus 0 times x plus 0 times x squared, so 1, 0, 0. Next, coordinates of T of x, T of the second basis vector. We have minus 5 times 1 plus 3 times x plus 0 times x squared. And then finally, 25 times 1 minus 30 times x plus 9 times x squared. And then that's the hard work done. As soon as we know this, we can write down the answer. We are asked to calculate the matrix for T relative to this basis B. We know the 3 columns of this matrix already. First column 1, 0, 0, second column minus 5, 3, 0, and third column 25 minus 39. Let me write this matrix in the yellow box. Question 2, we are asked to calculate T of 1 plus 2x plus 3x squared. And this polynomial has coordinate vector 1, 2, 3. So the coordinates of T of P is going to be the matrix for T multiplied by the coordinates for P. So that's a matrix multiplied by a vector, and I'll leave it for you to check that we get this vector, 66 minus 84, 27. As soon as we know the coordinates for T of P, we can write down T of P. T of 1 plus 2x plus 3x squared, 66 times 1 plus minus 84 times x plus 27 times x squared. And you can check this if you wish. If I go back to the questions. If you start with 1 plus 2x plus 3x squared and you replace every x by 3x minus 5, so it's going to be 1 plus 2 times 3x minus 5 plus 3 times 3x minus 5 squared. Put those in and multiply it all out, and you can check that we get 66 minus 84x plus 27x squared. And you might say, well, maybe that calculation is just as quick as this one. But if we start getting to bigger and bigger polynomials, instead of a secondary polynomial, let's suppose we have a 25th degree polynomial or 1000 degree polynomial, etc., then using the matrices and using this method will be an easier calculation. Using matrices is also a method which is easier to program into computers. Computers can be taught to multiply. Computers know how to multiply matrices together. If you know the matrices you have, put them into a computer, you get the answer quickly. If you try to teach a computer how to factor out polynomials, how to multiply out polynomials, that's going to take you longer. Next idea, compositions and inverses. Let's suppose we have two linear transformations, T1 and T2. T1 maps from U to V and T2 maps from V to W, where U, V, and W are vector spaces. And let's suppose we have bases A, B, and C for these three vector spaces. Then the theorem tells us that the matrix for T2 composed with T1 is equal to the matrix for T2 multiplied by the matrix for T1. And if I can just mention about notation first of all. Again, because we write it this way with the basis for the domain on the right and the basis for the target on the left, we have the b's next to each other. We can sort of imagine these two b's in the middle cancel out somehow, and we'll be left with C and A. So that's another reason why we're writing basis for the domain on the right and basis for the target on the left. Another theorem, if T is a linear operator, so that means domain is the same as the target, and if B is a basis for V, that same basis for domain and target, then the following are equivalent. T is 1 to 1, is equivalent to the matrix for T relative to B is invertible. And we can go further. We can say if this is true, if we know that T is 1 to 1, or if we know that our matrix is invertible, then it's true that the matrix for T inverse is the same as the inverse of the matrix for T. Let's do an example about a composition of two linear transformations. T1 maps from P1 to P2, and T2 maps from P2 to P2. T2 is a linear operator because the domain and the target are the same. And we'll use the same ones we've used before. T1 is going to be the linear transformation which takes a polynomial and multiplies it by x. And T2 is going to be the linear operator which takes a polynomial and replaces every x by 3x minus 5. We are asked to find the matrix for T2 composed of T1 with respect to the standard bases. So our standard bases are 1x, 1 and x, and 1 and x squared. We've done the work already here because we know that the matrix for T1 is 0, 0, 1, 0, 0, 1. And we know that the matrix for T2 is this one, 1 minus 5, 25, 0, 3 minus 30, 0, 0, 9. The matrix that we want, the matrix for T2 composed of T1, is just going to be the product of these two matrices. Multiply these two matrices together. First matrix for T2, multiply it by matrix for T1, and we get the answer. And that is a good place for me to take a break. I'm going to take a 10-minute break, and then I'm going to continue at 3 o'clock. And now let's continue. Our second topic for this week is the topic of similarity. Consider the matrix operator TA from R2 to R2, which has matrix 1, 1, minus 2, 4. Then the matrix for TA relative to the standard basis is just this matrix. The standard matrix for TA, or the matrix for TA relative to the basis B, is just A. It's just 1, 1, minus 2, 4. But we've seen that this is not the only matrix for a linear transformation. I want to calculate the matrix for the same operator TA, but relative to a different basis. I want to calculate the matrix for TA relative to this basis. The basis V1 is 1, 1, and the vector V2 is 1, 2. So as we were doing in the last section, we need to calculate T of V1 and T of V2, and then we need to find the coordinates for T of V1 and T of V2. We can calculate that T of V1, or A multiplied by V1, is 2, 2. That's just 2 multiplied by V1. And T of V2, the matrix A multiplied by V2, we can calculate is 3, 6, or 3 multiplied by V2. So we have that the coordinates for T of V1 are 2, 0, and the coordinates for T of V2 are 0, 3. So therefore, the matrix for TA relative to the basis C is this diagonal matrix, 2, 0, 0, 3. We have two different matrices for the same linear transformation. And let's look at the similarities and the differences between these two. Both of these matrices have determinant 6. Both matrices are invertible. The trace of both matrices is 5, but there's an important difference here. The latter matrix is a diagonal matrix, and if you recall when we were talking about diagonal matrices earlier, diagonal matrices are much easier to deal with. If, for example, I said, find this matrix to the power 13, straight away you could write this down. It's just 2 to the power 13, 0, 0, 3 to the power 13. Very quick. But if I said find the first matrix to the power 13, then that would be a long calculation to do. So hopefully that motivates the ideas in this section. If A and B are square matrices, then we say that B is similar to A if and only if there exists an invertible matrix P such that B is equal to P inverse AP. And I want to prove that if B is similar to A, then A is similar to B. And we can prove it like this. Let's start by supposing that B is similar to A. So in other words, we're going to start by supposing that B is equal to P inverse P, and then we're going to let Q be equal to P inverse. So then Q is an invertible matrix, and we have B is equal to QA, Q inverse, but that just rearranges to A is equal to Q inverse BQ, and that proves that A is similar to B. So instead of saying a matrix is similar to another matrix, from now on we could just say that two matrices are similar to each other, or two matrices are similar. Theorem: if A and B are similar matrices, then they have the same determinant. Let's prove this. If they are similar matrices, then we know that there exists an invertible matrix P such that B of P inverse AP, B is equal to P inverse AP. But then the determinant of B must be the determinant of P inverse multiplied by the determinant of A multiplied by the determinant of P. Anytime we have matrices multiplied together, we take the determinant. We could just take their determinant first and then multiply them together. But recall, we know what the determinant of P inverse is. The determinant of P inverse is just 1 divided by the determinant of P. So of course that cancels out with determinant of P and we're just left with determinant of A. I need a lemma, a small theorem. If A and B are square matrices of the same size, then the trace of AB is equal to the trace of BA. These don't need to be similar matrices, these are just any square matrices of the same size. Then the trace of AB is the same as the trace of BA. Let's prove this. First of all, what does trace mean? Trace means we take the entries on the main diagonal and then we add them together. So the trace of AB is going to be the entry AB11 plus the entry AB22 plus the entry AB33, etc. We're just adding the entries on the main diagonal. But how do we calculate these when we multiply two matrices together? Which terms are we doing? Which calculation are we doing to calculate these? Well, for example, if I wanted to calculate AB22, then I take the second row of the first matrix and the second column of the second matrix. Now note the first numbers are always the same, 2, 2, 2, and here in the second matrix, the second numbers are always 2. That gives us our 2, 2. But the first numbers change. The first numbers go, so second numbers in the first matrix, that's 1, 2, 3 up to n, these are changing. And in the second matrix, the first numbers are changing, 1, 2, 3 up to n. Now, what we do when we multiply two matrices together is we do A21 multiplied by B12, and then we do plus A22, B22, plus A23, B32, and so on. So basically what we're doing is we're multiplying Aij by Bji for all j between 1 and n. And we could do the same thing for the trace of BA. For the same reason, the trace of BA is going to be the sum of all the I, sum of all the j, Aji, Bij. And I want to show that that is the same as the trace of AB. And it's just a case of renaming the indices. First, let's replace all of the j's by a k, and then replace all of the i's by j, and then replace all of the k's by I. And then we get exactly what we want. We get Aij Bji, which is the same as the trace of AB. There's one small difference here in that we're doing sum over j first and then sum over I second, but that doesn't matter because these are finite sums. We can swap the order of these without any problem, and we get the trace of AB. I've done this because I can use this to prove the next theorem. If A and B are similar matrices, then they have the same trace. Now remember, we've just proved that the trace of xy is the same as trace of yx. We're going to use that to prove that if A and B are similar matrices, then the trace of A is the same as the trace of B. So similar to the way we did for the determinants proof, we're going to start by supposing that B is equal to P inverse AP. So we want to calculate the trace of P inverse AP. And I'm using the formula at the top. I've carefully done the colors. P inverse A, I'm going to imagine as one matrix X, and P will be my orange matrix Y. And the previous lemma said we can swap these. Instead of green, orange, we could have orange and then green. This is the same as trace of P inverse A. But P inverse, of course, just cancel out, and we're left with the trace of A. Let's talk about transition matrices again. Transition matrices is a topic which is covered by the first midterm exam. Let's suppose B and C are two bases for one vector space V. And I want to remind you of some of the ideas we've seen before. The change of coordinates matrix, or the transition matrix from B to C, is this matrix. It's P, and then underneath the P, B arrow C, or C arrow from B. This is the matrix where the first column is the coordinates of B1 with respect to the basis C. Second column is coordinates of B2 with respect to the basis C, etc. And we could go the other way. Instead of going from B to C, we can go from C to B. The change of coordinates matrix, or transition matrix, from C to B, that's P, and then arrow from C to B. First column is C1, coordinates of C1 with respect to basis B, and then coordinates of C2, etc. You will recall that these matrices are inverses of each other. The inverse of the first matrix is the second matrix, inverse of the second matrix is the first matrix. And the way that we were using these is, if we go from B to C, we could use the change of coordinates matrix from B to C, multiply that by the coordinates for some vector V with respect to B, and we would obtain the coordinates for V with respect to C. Or going the other way, P from C to B multiplied by coordinates for V with respect to C gives us the coordinates for V with respect to B. Everything on this side should be revision for you, and the topics on this side, on this slide, may appear on the first midterm exam. Theorem. If B and C are bases for a finite dimensional vector space V, and if I is the identity operator on V, then P from B to C is the same as the matrix for I with respect to the bases B and C, and P from C to B is the matrix for I with respect to the bases C and B. And there's another reason why this is a nice notation. P has C on the left, and the matrix for I has C on the left. P has B on the right, and I has B on the right. Matrix for I has B on the right. So let's prove this theorem. I'm going to prove the first formula. I'm going to prove that the matrix for I with respect to the bases B and C is the same as the transition matrix from B to C. Now, remember, the matrix for I with respect to the bases B and C, we have first column I of B1 with respect to C, second column I of B2 with respect to C, and so on. But because I is the identity operator, I of V is the same as V. So that means I of B1 is just B1. I of B2 is just B2, etc. We get the matrix where the first column is the coordinates of B1 with respect to C, second column is the coordinates of B2 with respect to C, etc. But that is exactly P from B to C. I've proved the first formula, and then I'm just going to say we could prove the second formula in exactly the same way. Let's talk about the effect of changing bases on matrices of linear operators. Let's suppose that B and C are two bases for a finite dimensional vector space V, and let's suppose that T is a linear operator on V. The question we want to look at is what relationship, if any, exists between the matrix for T relative to the basis B and the matrix for T relative to the basis C. Now, I want to think of it like this. Let's suppose we have 4 copies of our vector space V. On the top 2 vector spaces, we're using the basis C, and on the bottom 2, we're going to use the basis B. Looking at the bottom 2 vector spaces, and first, we have our linear operator T, which maps a vector V to a vector T of V. And this linear operator has matrix square bracket T square bracket B, because we're using basis B on both the domain and the target. Now look at the top 2 vector spaces. Again, we have our linear operator T, which maps the vector V to the vector T of V. But now, because we're using the basis C, we have a different matrix. We have square bracket T square bracket C. And the left 2 and the right 2 vector spaces are connected using the identity operator. Now note that orange line, orange arrow, is the same as doing red, then green, then brown. Brown I composed with green T composed with red I is the same as doing orange T. So their matrices must be the same. The matrix for T with respect to C must be the matrix for I composed with T composed with I with respect to C. But as we've seen, if we're doing compositions of linear transformations, we just multiply their matrices together. So that's the matrix for the brown I with respect to the bases B and C multiplied by the matrix for the green T with respect to the basis B multiplied by the basis for the red I with respect to the bases C, B. But remember, the matrix for the identity operator is just our transition matrix or our change of coordinates matrix. So that gives us this theorem. Let T be a linear operator on a finite dimensional vector space V, and let B and C be bases for V. Then the matrix for T with respect to the basis C is equal to P inverse multiplied by the basis, the matrix for T with respect to the basis B multiplied by P, where P is the transition matrix from C to B, and P inverse is the transition matrix from B to C. Now, we started this section by talking about matrix is equal to P inverse matrix P, when we started talking about similar matrices. This theorem tells us that if we have two matrices representing the same linear operator, then they must be similar. And in fact, we can go further than this. It's not just implies, it's if and only if. Two matrices, A and B, represent the same linear operator if and only if A and B are similar. This is an idea we're going to come back to again in future lectures. But for now, let's completely change topic. That's enough of linear algebra for this week. For the rest of today's lesson, I want to talk about numbers, and in particular, I want to talk about complex numbers. So, for the time being, put all of the linear algebra out of your mind. You can forget about matrices, you can forget about linear transformations. We're just going to be talking about numbers now. And we'll start by talking about the first numbers that children are taught. The numbers 1, 2, 3, 4, 5, 6, etc. are called the natural numbers. So for example, 2 is a natural number, 7 is a natural number, a half is not a natural number. For the next one, there is a little bit of disagreement about in the world. There are some mathematicians in the world that think that 0 should be a natural number, but most of us agree, by far the majority of us agree, that 0 should not be a natural number. It's possible that one of your teachers in the past was in the minority and said that 0 is a natural number, but I'm saying it's not. And most of the mathematicians in the world would agree that 0 is not a natural number. And negative numbers such as -5 are not natural numbers. In the natural numbers, we can do two things. We can do plus and we can do multiplication. By that I mean, if we take two natural numbers, for example 2 and 7, if we add them together, we still have a natural number. If we do natural number multiplied by natural number, then we have a natural number. But as we learn when we were small children in our first school, we can't always do subtraction in the natural numbers. Sometimes, if we do natural number minus natural number, we don't get a natural number. So, what do we do? What did humans do in our history when humans only had natural numbers? Our ancestors invented new numbers. And what they did was they invented 0 and negative numbers. If we take our natural numbers, 1, 2, 3, 4, 5, 6, etc., and we add in 0, and if we add in the negative all of the natural numbers, then we get numbers which are called integers. Now, the way I want to think about this is the natural numbers are numbers which exist in the world. We could count things. We could have 7 cakes or 3 stones or 12 pens. We could have whichever objects we have in front of us, we could count them, and this would be natural numbers. The other numbers here, 0 and the negative numbers, were invented by humans. It's not possible to have -3 cakes. But we accept this because we've been studying negative numbers and 0 at school and at university for so many years. We're happy with them. Most people forget that 0 and the negative numbers are invented by humans. They just think of them as normal numbers. In the integers, we can do addition, subtraction, and multiplication. But we can't do division always in the integers. Why? Well, sometimes we do integer divided by integer and we don't get an integer. So what do we do? What did humans do in our history when they realized this problem? we invent new numbers. And the numbers that humans invented were the rational numbers, or the fractions. So, for example, 0 is a rational number because 0 is 0 divided by 1. 1 is a rational number. 3/4 is a rational number, but pi is not a rational number. Proving that goes beyond the scope of this course. 100/13, that's a fraction, so that's a rational number, but the square root of 2 is not a rational number, and so on. In the rational numbers, we can do the 4 operations. We can do addition, we can do subtraction, we can do multiplication, and we can do division, as long as we're divided by a number which is not 0. So I ask, are we happy now? Do we have enough numbers to be able to do mathematics? And the answer is no. Why? Why are we not happy? Why are the rational numbers not enough numbers to be able to do some serious mathematics? And the answer is, if we try to draw all of the rational numbers in a line, then our line is going to have lots and lots of holes in it. In fact, Q is going to have infinitely many holes in it. So what do we do? What did humans do in our history? Again, humans invented new numbers. And the numbers that humans invented were which we now call the real numbers. That's all the numbers which can be written as a decimal. And this is actually a bad name for these, because these are not real. Only the natural numbers are the numbers which really exist in the world. These are invented numbers. So it's a bad name to call these real numbers. The real numbers are complete. That means if we draw all of the real numbers in a line, then there would be no holes in the line. So are we happy now? Do we have enough numbers to be able to do mathematics? We have enough numbers to be able to do calculus. Those of you who've taken my calculus courses would note that I would finish here, but we're not doing calculus, we're doing linear algebra. And for linear algebra, we don't have enough numbers. Why? Because not every polynomial has a root in the real numbers. For example, there's no solution to x squared plus 1 equal to 0 in R. So what do we do? What did humans do in our history when we realized this problem, when we realized we don't have enough numbers to be able to do mathematics? So we invent new numbers. And the number that we invent is called I. And we invent this so that it is a solution to the equation I squared plus 1 is equal to 0. Or to say this another way, we say that I squared solves I squared is equal to minus 1, or I is the square root of minus 1. Now, let me just point out, I is a made-up number. I was invented by humans. We can't have I cakes or I pens. We can't have some objects in front of them and count them and get the answer I. But as I've tried to explain, 0 and minus 3 and 7/8 and pi, these are also made-up numbers. These were invented by humans. 0, the negative numbers, fractions, irrational numbers, etc. These are all inventions of humans. But we accept them because they're useful to us. We've been studying these numbers for, well, I don't know how old you are. I imagine you've been studying these numbers for at least 10, probably 15 years you've been studying these numbers. So you accept them. You accept that these are numbers, you're happy with these, but please understand from now on that these are inventions of humans. We can't count the number of cakes we have in front of us or number of stones we have in front of us and obtain the answer we have pie stones in front of us. Now, somebody might say, wait a minute, let's suppose I have a cake, and let's suppose I cut the cake into two. Then I have half cakes. But my answer to that is no. You don't have two half cakes, you have two small cakes. You can still count how many cakes you have, count 1, 2. You only think that you have half cakes because you've been studying fractions through most of your academic life. We accept fractions, negative numbers, etc., because they're useful to us, but I is also useful to us. We can't do any more linear algebra until we're happy with the number I. Now that we have this number I, we can start working with numbers like these: 3 plus 4i, 2 plus 7i, minus 12i, etc. A complex number is any number which can be written as a plus bi, where I solves the equation I squared plus 1 is equal to 0, and a and b are real numbers. The set of all complex numbers is written like this. It's a hollow capital C. For real numbers, if there's just some number, we usually use the letter X. For complex numbers, we usually use the letter Z. So we can be writing things like Z is equal to A plus BI. The first real number, the A, is called the real part of Z. We write that as RE, capital R, small e, of Z. And the second real number, the B, is called the imaginary part of Z. And we write that as capital I, small m, of Z. So, for example, the complex number minus 2 plus 7i has real part minus 2 and imaginary part 7. The complex number 7i has real part 0 and imaginary part 7. And the complex number minus 2 has real part minus 2 and imaginary part 0. An imaginary number is a complex number a plus bi, where a is 0. So, for example, minus 12.2i, or square root of 2i, or 7i, these are our imaginary numbers. A real number is a complex number a plus bi, where b is equal to 0. So, for example, 3, root 5, minus 12.2, etc. These are real numbers. And all of the numbers I've written here are complex numbers. These names are really bad names. These names come from the 17th century, and that comes from their understanding at the time. At the time, more than 300 years ago, people were thinking that real numbers were somehow existing in the world or real, and they thought that these imaginary numbers were the made-up ones. But now we know that almost all of the real numbers are just as imaginary or made up as the imaginary numbers. But these are the names that we're stuck with. These are the names which have persisted for more than 300 years, and it's too late to change them to better names now. So, how can we think of complex numbers? Well, real numbers we like to think of as a line, but I is not a real number, so I is not on the line. I is somehow away from the line. We can think of complex numbers as a two-dimensional plane. We have our real numbers along the horizontal axis, and we have the imaginary numbers along a vertical axis. And then every other point in the two-dimensional plane we can think of as a complex number. For example, 2 plus I is here in the plane. Minus 3 plus 2i, we can think is here. I, 0, 4, minus 2i, we can again imagine as points in the two-dimensional plane. Now that we have I, we can take the square root of any negative number. If we were asked to find the square root of minus 9, we can remember that's minus 9 is 9 multiplied by minus 1. And if we're doing the square root of a product of two numbers, we can just do square root of 9 multiplied by square root of minus 1. So just 3i. We can add two complex numbers together in the obvious way. 2 plus 3i plus 1 minus 6i. We take the real parts, 2 and 1, add them together. We take the imaginary parts, 3 and minus 6, add them together, and we get our answer, 3 minus 3i. Very easy. Likewise, we can multiply two complex numbers together in the obvious way. 2 minus I multiplied by 3 plus I. Just as if we were doing A plus B multiplied by C plus D, we just multiply out the bracket. So first numbers, 2 and 3, multiply them together. And then multiply first by second, 2 multiplied by 4i, and then second by first, minus I multiplied by 3. And then finally second by second, minus I multiplied by 4i. We have 6 plus 8i minus 3i minus 4i squared, but I squared is just minus 1. So minus 4 multiplied by minus 1 is just plus 4. The answer is 10 plus 5i. We can do complex number divided by complex number, but we need a trick. And this is a trick which I hope you remember from Calculus 1 when you were using this trick to calculate limits. If we're doing divide by 2 plus I, change the plus to a minus, we need to multiply by 2 minus I divided by 2 minus I. And the reason we're doing that is that so on the bottom, minus 2i plus 2i will cancel out, and we'll just be left with a number on the bottom, the number 5, a real number. 3 minus I divided by 2 plus I is equal to 1 minus I. Any number to the power 0, any non-zero number to the power 0, I should say, is equal to 1. So I to the power 0 is 1. I to the power 1 is I, that's just here. I squared is equal to minus 1. I cubed, multiply left and right by I, is minus I, because that's minus 1 multiplied by I to the power 4, again, multiplied by I, we get 1. Look at the pattern that's going on here. Look at the spot on the picture. I to the power 5 is I to the power 6 is minus 1, I to the power 7 is minus I, and so on. I to the power 8 is 1. Go round and round the circle. Let's take any complex number. Z is equal to A plus BI. It exists somewhere in the complex plane. The two axes on the complex plane, I'm calling the real axis and the imaginary axis, because the real part of Z is the number A, and the imaginary part of Z is B. So if we projected our point onto the axes, we will get the number A and the number BI. The distance from the origin to Z we call absolute value of Z, or the modulus of Z. And of course, that's square root of A squared plus B squared. the angle here, the angle between the real axis and this dashed line, if we measure the anti-clockwise direction, is called the argument of z. And if we do the reflection by the real axis, so in other words, we take z and we reflect it down here, we get a new complex number which is called the complex conjugate of z. If z is a plus bi, then the complex conjugate of z is a minus bi. And complex conjugate is going to be important to us. Note that if we multiply z by the complex conjugate of z, so that's a plus bi multiplied by a minus bi, complex conjugate, we take plus it, whichever we have in front of the I, and we change it to the other side. So plus becomes minus and minus becomes plus. If we multiply this out, we get a squared plus b squared, which is just the modulus of z squared. I also want to remark that the only way that we can have z equal to its own complex conjugate is if z is a real number. Why? Because if a plus bi is equal to a minus bi, the a's cancel, and then we can divide by the i's. That's only true if b is equal to 0. It is a fact that the complex conjugate of zw is equal to the complex conjugate of z multiplied by the complex conjugate of w. I'm not going to prove that. I'm going to leave that for you to prove. And I'm going to finish by talking about some roots of polynomials. If we had the equation x minus 5 equal to 0, we know the solution of that. We know that the solution of this equation is x equal to 5, and that's a number which is in the natural numbers. If we had the simple equation x plus 2 equal to 0, then its solution, x is equal to minus 2. Which set is minus 2 in? Minus 2 is in z. What's the smallest set, I should say, that minus 2 is in? If our equation was 2x minus 1 is equal to 0, this equation has solution x equal to a half. To be able to solve this equation, we need to move to the rational numbers. If our equation was x squared minus 5 equal to 0, then the solutions are plus root 5 and minus root 5. These are not rational numbers. To be able to solve this simple equation, we would need to use the real numbers. We need to invent the real numbers. And to solve x squared plus 1 equal to 0, we need the complex numbers. These are all very simple equations. We just have plus, minus, multiplication, division, and powers in these equations. There's nothing complicated going on, it's just these 5 operations. And the numbers in these equations are all very simple, 5, 2, 1, etc. Now, you might ask, are there any numbers after C? We've gone from the natural numbers, that wasn't enough, so we invented integers. Integers wasn't enough, we invented the rational numbers. Rational numbers weren't enough, so humans invented the real numbers, and then after we realized that the real numbers weren't enough, humans invented the complex numbers. So the question is, are there any numbers after C? Just doing these simple equations. And the answer is no. And that brings me to the final slide of today's lesson, the fundamental theorem of algebra. When you're studying mathematics, anytime your lecturer calls a theorem the fundamental theorem of something, then you know it's going to be an important one. In Mathematics 1, we had the fundamental theorem of calculus. Now I'm stating the fundamental theorem of algebra. And this theorem says Any polynomial with complex conjugates will only have complex roots. So what this means is that if we just have the 5 operations, if we only can do plus, subtraction, multiplication, division, or powers of a number, then we can't make any more numbers. The complex numbers is the end of the line. And now we're happy. Now we have enough mathematics to be, now we have enough numbers to be able to do some serious mathematics. Now we can do our linear algebra. Next week, we do not have a lesson. So in 2 weeks' time, I'm going to start talking about eigenvalues and eigenvectors, diagonalization of matrices, and the reason that I've been talking about complex numbers today is that next lecture, we're going to start talking about complex vector spaces. Are there any questions?